Hello my students, your physics teacher Hassan Darwish with you. In this video, I'm going to solve exercise 1 in the revision exercises of chapter 17 about hydrogen atom. Now the energy levels of this atom are given by this expression, minus 13.6 over n squared, where the energy is in electron volt and n is a whole number. We have the given. Part 1, this expression of En shows that the energy of the atom is quantized. What does the term quantized mean? So since En depends on n, that is a whole number, En takes only specific and discrete values, right? I mean not any value. Hence En is quantized, okay? Now part 2, calculate the energies of corresponding to the levels n equal 1, n equal 2, n equal etc. up to infinity. You just have to replace here n equal 1 here. You get the energy of the first level, which is the ground state level. N equal 2 here, you get the energy of the first excited state. And n equal 3, you get the energy of the second excited state, etc. For n equal infinity, the number over infinity is 0. Then this is called ionization energy level or ionization state of the atom. Okay, let's do this. N equal 1 minus 13.6, n equal 2 minus 3.40, 3, etc. Okay? Now in part 3, draw a diagram which represents the energy levels of the hydrogen atom. You know the diagram. This is called energy level diagram. And we do it like this. This is the vertical axis which represents the energy of the hydrogen atom. Now here for n equal to 1 minus 13.6, n equal to minus 3.4, etc. Okay? Part 4, the Lyman series is a set of emitted rays, means emitted photons, corresponding to the transition of the atom from the excited state to the ground state. He means from any excited level to the ground energy level. Okay? Part 4.1, calculate the greatest and the smallest wavelength in this series. Means calculate the longest wavelengths of the photon and the smallest wavelengths of the photon in this series. Okay? Let me tell you something important first. Here, I use red. Every time the photon jumps, the electron jumps from the level to the ground state, we get a released photon. Okay? So here in part 4, Lyman series, as he defined it and as we know, is the transition from any excited level to n equal to 1. So in Lyman, we must have a jump from n equal 2 to n equal 1, 3 to 1, 4 to 1, etc. up to infinity. We need the smallest wavelength and the biggest wavelength. Okay? You know that when the atom undergoes a transition from an excited level to a lower level, we have a released photon, and the energy of the photon is given as E of the photon equal E final minus E initial, right? E initial minus E final. Initial is any level here, 2, 3, 5, 10. Final is the ground state, because this is what? Lyman series. Okay? So to get the longest lambda we have, okay, but first let's find the energy of the photon. Energy of the photon is hc over what? Lambda. It means lambda equal hc over energy of the photon. So lambda and energy of the photon are inversely proportional. To get longest lambda, you must have smallest photon, right? Smallest energy of the photon means smallest difference here, right? But look at the diagram here. Where is the smallest difference between 1 and which level? Between 1 and 2, right? So when we have a jump from 2 to 1, you get the energy of the photon. But this energy of the photon is the smallest because this is the smallest gap, smallest space. If the energy of the photon is smallest, then the wavelength is longest, since they are inversely proportional. Okay? So here En minus E1 is smallest. Smallest from 2 to 1. You subtract the energy, you get 10.2. So lambda longest, replace H and C and energy of the photon. You change it into electron volt, from electron volt to joules. Then you get this number, 122.5 nanometer. Okay? You need now the shortest. This is the longest. We need the shortest. The same calculation. Okay? The shortest lambda, the greatest energy of the photon. Greatest energy of the photon means the biggest En minus E1. Where is the biggest En minus E1? Here. Biggest space from infinity to 1. Right? You get the biggest energy of the photon means the smallest wavelength. So similarly, from infinity to 1 and do the same calculation, you get 91.91 nanometer. Notice here, this number and this number are less than 400 nanometer. It means all the wavelengths in this range, I mean in Lyman, lie or fall in the ultraviolet range. They are invisible wavelengths. Okay? All of them are ultraviolet. Now, part 4.2. Show that the wavelength of a ray, he means of a photon also, or of a wave, in the Lyman series is given by this expression. You have to prove this expression, where RH is called Rydberg constant. Okay, we remember this when we studied the hydrogen emission spectrum. Let's do it here. Of course, we have to apply Bohr's formula. From any energy level n to n equal to 1, this is Lyman. Final level in Lyman is ground level, ground state. E energy of the photon equal E initial minus E final, right? Look here. E photon equal E initial minus E final. Final is 1. Initially is any level here. And you know the energy of the photon here is hc over lambda, right? Here it is. So if you do the calculation, take here 13.6 as common factor between this and that, and then divide by hc. Look here, I have changed hc 13.6 from electron volt into joules. You multiply by 1.6 times 10 to the power minus 19. This is a constant number, right? So this is RH, Rydberg constant for the hydrogen atom. Okay? Do the calculation for this RH, you get 1.095 times 10 to the power 7 inverse meter. Why per meter? Because here we have 1 over lambda, and the unit of lambda is meter. So within experimental error, it is the same number obtained by Balmer and Rydberg. Now, the H atom is in the ground state. it receives monochromatic radiation of wavelengths 102.82. The atom is then excited. Determine the new state of the atom. We have to remember the absorption process. The atom only absorbs the photon that it emits. Clear? Now because this atom absorbed this photon, then it is able to emit it. So, but the process is inverse. So here is the H atom in the ground state, means n equal to 1 initially, absorb this photon. Clear? Because it absorbed this photon, then it is able to emit it. Don't forget this. So E of the photon equal E final minus E initial. Notice here absorption, which is opposite to emission. E initial minus E final. So do the calculation and don't forget to change this into electron volt. Many students forget to change because the unit here is electron volt and the unit here is joule. So change electron volt, joules into electron volt by dividing by 1.6 times 10 to the minus 19. You get minus 1.5. 1.5 here is the level, 1.5. Here it is, 1.5. Here it is. Means to n equal 3, okay? So it is excited to n equal 3 means second excited state. Now 5.2, draw on the energy level diagram the possible transition of the atom during the excitation. Now the atom is excited here to this level. Let me draw it by blue. The atom is excited to this level. Now what are the possible de-excitation? It either fall directly from n equal 3 to n equal 1, then you give a photon of certain wavelength, or it falls from n equal 3 to n equal 2, then from n equal 2 to n equal 3. So here we have in this process 2 photons. So the probability is directly falls to 1 or in 2 steps, 3 to 1, then 3 to 2, then 2 to 1. Okay, we have 2 possible photons. Okay, 3 to 1 directly, or 3 to 2, then 2 to 1. Okay? Now, a photon of energy 10.8 electron volt hits the hydrogen atom in the ground state. Don't forget the state here, ground state. The atom does not absorb this photon. It means it does not emit this photon. Justify. And as I said, an atom absorbs only the photon that it can emit. Clear? When it is excited. So we apply the rule. Case of absorption, E photon equal E final minus E initial. We find the final state of the atom. It is minus 2.8 electron volt. But look at the diagram. Does this energy exist here? It doesn't. Minus 2.8 doesn't exist here. Means this the atom cannot absorb this photon. Okay? So the final state of the atom minus 2.8 does not exist. So this photon is not absorbed. Okay? Now, an electron of energy 10.8 electron volt collide with a hydrogen atom in the ground state. The atom releases a photon of wavelengths 121.87. To which energy level is the atom excited? Justify. Here, initial kinetic energy of the electron emitted photon, this. So an amount of energy equal to the energy of the emitted photon is absorbed by the atom from the electron, right? So the atom only absorbs the amount of energy of the photon that it can release. That's why we find E of the photon. This is the final state of the atom, minus 3.4, means for n equal 2.